Hi. So today I'm going to explain the questions that you are given. We'll discuss this about. So let's start with the 9.37. In this question, you see that it's written as a 5-meter diameter parachute of a new design is to be used to transport a load from flight altitude to the ground with an average vertical velocity or speed is 3.3 meter per second. The total weight of the load and parachute is 200 Newton. Determine the approximate drag coefficient of the parachute. So it asks us to determine the drag coefficient for this parachute. Now, for the drag coefficient, we know the equation, right? CD equals to D divided by half rho P square by multiplied by A. Now it says that average vertical speed of 3 millimeter per second, right? That means we can assume that it's in equilibrium at constant speed. If that's the case, then the weight and the drag force will be the same, right? So we can write CD equals to D equals to, if D equals to W, then we can write CD equals to W by this one. Now for weight is 200 Newton, right? Half multiplied by rho, because this is going through an air, right? So we can use the air density, and then v square. We know the v equals to U equals to 3 meter per second, and A is the area. So area is 5-meter diameter, it says, right? So it should be 5 by 4, 5 square. Basically, it's a circular shape. So the CD is 1.84. The sea level density was used here to solve this problem. So basically, if this parachute is moving from one point to another, so there is a little change in density of air, but we assume that it's a constant. Okay, that's the one assumption. So that's it. That's for the question number 9.37. Now let's go for the question number 9.39. This question says the aerodynamic drag on a car depends on the shape of the car. Yeah, we know this. So for example, the car shown in figure this has a drag coefficient of 0.36 with the windows and roof closed. So you see this one is closed, right? Windows and roof. And it has a drag coefficient of 0.3. Oh, okay. It should be 0.36. Okay, it's just a printing mistake. With the windows and roof open, for example, this one, the drag coefficient increases to 0.45. You see the 0.45, these are open. Now with the windows and roof open, at what speed is the amount of power needed to overcome aerodynamic drag the same as it is at 65 mile per hour with the windows with roof closed? So that means it says that at what speed, so we need to calculate the speed, that is U, the amount of power needed to overcome. So the power should be the same for both of these cases, right? Uh, so the power should be the same, but the velocity of with the windows roof closed, that means this one will be 65. So that means, if this car can go at 65 mile per hour, then it will produce some drag force. And that drag force, to overcome this drag force, we need the power, right? That power will be the same as this power. Then we need to find out the velocity of this car. And it says that the power is force times velocity. So if it says force times velocity, so we know P equals to power equals to F multiplied by V. Now we have two cars, open and closed. Sorry, this one is open, this one is closed. So we know that for drag force, you can use this equation, D equals to CD multiplied by half rho U square multiplied by A, right? Now, let's say for open car, the power is P naught. So U naught, V naught, D naught, right? because F and D is same. So U naught, D naught. That means half. This is for open curve. Okay, this is for open curve, and we're calculating the power. Power equals to U multiplied by F. So F is replaced by D because drag force is the force that should be used. So then use the value of D naught equals to here. Now this will be the same as the power needed for the closed curve. So for closed curve power is PC, and that can be written as UC DC. So that's one. Now if we equate these two equations, then we should get, because the rho is same, so that will be cancelled out, right? Half cancel out. So U naught Q multiplied by CD naught, right? Now, and the A naught and AC, this will be the same because the frontal area are the same. It was not changed. So that will also cancel out. So U naught equals to UC multiplied by CDC divided by CD naught whole to the power 1/3. Now UC closed car that has a velocity of 65 mile per hour multiplied by CDC, these are given. So that's how we calculate the U naught. Okay, so that's for question number 9.39. Let's go for the next question. So the next question is about 9.43. This question says that a sphere of diameter d. So this sphere has a diameter d and the density is rho s. It falls at a steady state, okay, through a liquid of density rho. So that's in a solid state density is rho s, but the liquid's density is rho and viscosity is mu. If the Reynolds number is this equation, which is less than 1, then show that the viscosity can be determined from mu equals to this equation. So we need to derive an equation that can be used to calculate the viscosity, and that should be the same as this one. Now it says that the this sphere is falling in a steady flow. Steady flow means there is any acceleration. That means summation of force will be 0, right? Summation of force equals to 0, then we know that gravitational force acts on downward, and drag force and buoyant force works on top upward. So it should be the same. Drag force, buoyant force equals to gravitational force. Now we just need to put the value of of these three. Buoyant force equals to rho z 4 by 3 pi multiplied by d by 2 whole cube. So they just put the equation. Yeah. Weight mz, m equals to rho s z. Rho s is the density of this sphere. So you just put the value, and the drag force equals to CD half rho pi by 4 d square. Now, if Reynolds number is less than 1, then this equation can be rewritten as d equals to 3 pi dp mean, right? We already saw this equation in the lab as well for Reynolds number less than 1. Now, if we put the value of d, w, and fp in this equation, we should get this one. And if you rearrange it, you'll get this mu equals to z d square multiplied by rho s minus rho divided by this. So that's what you can use to calculate the viscosity. It's the same as it was written here. So that's proof.